Okay, so I think it's good time to start. Myself, Harish. I am a PhD student at ISER Mohali, and I'm going to conduct the problem session for this algebra second course. So we have already revised lecture week one and week two notes, and last time we saw the solution for uh, this assignment 1, and today we will see assignment 2. So yeah, I hope my voice is clear and the screen is visible too.
Yes, sir.
Okay, thank you, Vivek. So let me just make it plain. Okay, so we're going to see this is our week 4, right? Week 4. So we are supposed to discuss assignment 2, but last time I remember that we were left with one question of assignment 1. So I will just uh, start with that, and then uh, we will move to assignment 2 also. Let me just copy paste that question. Here it is. It says, for which of the following fields are all elements constructible? So we have seen already many questions related to the constructible numbers. So here it says that we have to choose the fields in which every elements are constructible. So first of all, this q root 3 root 8. So we know all rational numbers are constructible, right? So only thing to see is whether root 3 and root 8 are constructible or not. So for that, let's consider this. Consider the following tower of fields. This is for first one. Okay, some issue with this writing pad. Tower of fields. So here we have Q, and then as a it is a, you can see as a subfield it is root 3 root 5 or what, root 3 root 8. So it is contained in Q root 3 as a subfield, and then Q root 3 is lie inside Q root 3 root 8 as a subfield. So we just need to make sure that each of them are of the extension 2, are of degree 2. So from here uh, to here, definitely the degree is 2, since x square minus 3 is satisfied. That we have seen, I think, a number of times. It is satisfied by root 3, and it is irreducible. Hence, why it is irreducible? Because it has factors that are not inside Q. So it cannot be split into the linear factors, and thus it is irreducible because it's a polynomial of degree 2. So only way to split is to in linear factors. Similarly, here you can see that degree is 2 since root 8 is not inside uh, since root 8 is not inside Q root 3. Why? Because okay, I will say a few words on this. Uh, and with root 8 satisfies x square minus 8 in Q root 3 x. Okay, so it satisfies this polynomial, so definitely the degree has to be less than equal to 2, but it is not inside this field. That means its degree has to be greater than equal to 2. So both combinedly gives us the degree 2. So why it is not inside Q root 3? This is because so Q root 3 has elements of the form a plus b root 3.
B root 3.
Yes, and where AB are, so this is not of this form, AB are in Q. So as we did in the last lecture, that we showed that root 5 is not of the form a plus b root 3. Similarly, one can show that root 8 is not of the form a plus b root 3. Just square it, and if you square it, you will get 8 equal to a plus b root 3. Then 8 minus a is equal to b root 3. Now b cannot be 0. B cannot be 0 because if b is 0, then it is simply root 8 equal to a, which means root 8 is rational. A is a rational number. Na? So b cannot be 0. So from here, if you square, then it will be 8 minus 8 equal to the square of this. And then it's just, you can contradict by using that root 3 is a rational number. Okay, so if so happens, then you will ultimately get root 3 is rational, which is a contradiction. Okay, so that is a hint behind it. So now we have the uh, tower of fields. So how, so Q, each uh, rational number is each rational number is constructible. That is always true. And also root 3 is constructible due to this tower Q root 3 and Q. So last time we and it has degree 2. So last time we saw that if a number has a so if a number is constructible if and only if there is a tower of fields, each of which is of degree 2, and the number belongs to the topmost field, right? So this tower, for this tower, Q root 3 is here, root 3 is here, and it is just a degree 2 extension of Q, so it is constructible. And root 8 is constructible due to this tower. I should have make some space here. So this is Q. So root 8 is constructible due to the tower, the above tower. Okay. Q root 3 root 8 and then Q root 3 and Q root Q. Okay. So these are the only this implies each element of Q root 3 root 8 is constructible. Why is it so? See, Q is constructible. Q root 3 is root 3 is constructible. Now each element of Q root 3 is of the form A plus B root 3. Where A is constructible, B is constructible, root 3 is also constructible. So A plus B root 3 is constructible. So each element of uh, Q root 3 is constructible. Now Q root 3 root 8 is just a extension of it, degree 2 extension. So where root 3 is constructible, and now each element of Q root 3 root 8 will be of the form. So this contains elements of the form A plus B root 8, where AB are inside Q root 3. Okay, not Q, but in Q root 3, because we are taking as a degree 2 extension of this Q root 3. Then each element of Q root 3 is constructible, B root 3 is constructible, and root 8 is also constructible. So their linear sum will also be constructible. So that's the idea. So therefore, each element of Q root 3 root 8 is constructible. Okay. So that is first question. What about second?
Sir, it is isomorphic to Q root 3, I think. Oh, sorry, cube root of 3.
Cube root of 3. Yes. Then
And I think not under root 3 is not. This is cube root 3. So I think it will be not constructible.
why? You are very much on the right track. So this is isomorphic to Q 3 1 by 3 and also xi 3.
Yes, sir.
Right? So, just a second. So this is 3. Oh, no. So I think it will be just 3 1 by 3. Xi 3 is on this much is on. They can be written as product, and that's it. Xi 3, because one root is 3 1 by 3 xi 3. The other root will be 3 2 by 3 xi 3 square. It has three roots. First is 3 1 by 3. Then second is 3 1 by 3 xi 3. Third is 3 1 by 3 xi 3 square. So as an isomorphism to a field of this kind, I'm not sure whether we can write it or not. Because see, when we are quotienting it, this field t square minus 3, then we know that root 3 will generate
Yes.
other root also, minus root 3 also. Okay, but in this case, one root is not generating the other,
Yes, sir.
right? This 3 1 by 3 won't generate these two. These two are complex numbers, right? So
Yes.
as a field, whether we can write it like this or not, this is a bit doubtful for me. The other thing to see here is, uh, but this polynomial is definitely irreducible. This is a field of, uh, okay. So this polynomial is irreducible by Isochrone criteria, right? You can take prime to be 3,
Yes, sir.
and this implies t square minus 3 is maximal ideal, and which implies that this is a field, right? So although it's just a quotienting by a polynomial of a polynomial ring, but this is a field that is okay. Now, okay, let me write it here separately. That would be better. So, uh, what we used to do, consider the map phi of lambda alpha from qt to qt by tq minus 3, such that or maybe I'm missing something. It's from the other side. Qt to tq minus 3 to q of t, q of t, which should be some q of say maybe alpha I can write, or yes. So this polynomial, any polynomial pt will be mapped to p of alpha, right? Where um, alpha is a root of t cube minus 3. So in this way, we will get an extension alpha of this kind, and then this will implies that qt. So the what is the kernel of this map? Kernel of this map will be uh, all polynomials for which alpha is a root, right? So this will be generated by this only, and then I think this also we can remove. So just pt to p alpha, if we send the map, then this will implies the kernel of um, this phi alpha is what? Kernel of,
The kernel, I think, contains only three members now.
no,
That is the root
it
of.
contains polynomials. So this is from this is mapping the polynomials to the p of alpha.
All the polynomials.
Yes.
Q2 tends to
Here
Q
also
alpha.
you can remove alpha. You can just map from qt to q the polynomial No, alpha is not inside. Alpha is not inside this. Yes, yes, yes. So better thing to take here is maybe C. C will work. Okay. So
Like,
now kernel of Q alpha will be all those polynomial Pt such that P of alpha is 0, right?
yes, and now
So this is nothing but the ideal generated by T cube minus 3, because this is irreducible over Q. So it cannot have factors then. So smallest polynomial that satisfies alpha is T cube minus 3. That's why it's the ideal generated by 3. So first of all, this is a this has to be a, principal ideal. This has to be a principal ideal, since this is an ideal of Qt, and Qt is uh, a principal ideal domain. So each ideal has to be principal ideal. Thus, principal ideal means generated by a single element. So this has to be generated by a single element. Now T cube minus 3 is the irreducible element inside it. So it has to be generated by T cube minus 3. So this implies Qt modulo T cube minus 3 is isomorphic to the image of uh, phi alpha, and this is a field, of course, because T cube minus 3 is a irreducible one. And what is the image of phi alpha? This is nothing but all polynomials of the P alpha such that Pt belongs to Q of T, right? Now, this is, you can say this is same as A plus B alpha plus C alpha square such that A, B, C belongs to Q. Why? This you can, here you can use Euclid's division algorithm. So why is it so? So say you have a polynomial of degree greater than equal to 3. Then you can divide it by T cube minus 3, right? And so what I mean by using the Euclid division algorithm, for any polynomial of degree greater than equal to 3, so here let's say polynomial is fx. Okay, there exists gx belongs to qt such that your fx is gx, and also let's say hx also, gx comma hx in qt, oh sorry, gt and say ht. Here also it should be ft. So gt and ht in qt, here it is ft. Very bad. Okay, such that f of t, I have overused notations. So f of t is gt
P
pt
H P
plus ht,
plus H
and degree of ht is
less than or is equal to
2, right? Because pt is of degree 3. So this is what division algorithm says, right? The degree of this has to be less than, strictly less than the degree of pt. And degree of pt is 3, so it has to be less than equal to 2. So this implies that f of alpha is what? F of alpha is g of alpha
alpha
p of
P
alpha
alpha
plus
plus H
h of
alpha.
alpha. Now P of alpha is 0, right? Because alpha is the root of P. So this is nothing but h of alpha, which is a degree 2 polynomial in alpha. That's how we are getting it. Okay. So this is, so any element of this uh, field P alpha, this image of phi alpha is of the form A plus B alpha C alpha square, right? Okay.
Okay, sir.
Okay. So this is what your the description of this QT modulo TQ minus 3 is. A plus B alpha plus C alpha square, these kind of elements where A, B, C are in Q. So now can you say whether each element of it is constructible or not? It's not difficult. Observe that alpha belongs to uh,
So this is the element, na, A plus B alpha plus C alpha square.
these kind of elements are there where A plus B, A, B, C belongs to Q. So in particular, you can take alpha, right? Alpha means A you are taking 0, B to be 1 and C to be 0. So alpha belongs to this QT modulo TQ minus 3, right?
Mm.
So alpha belongs to this uh, and alpha satisfies TQ minus 3 over Q, right? Also, we know that TQ minus 3 is irreducible, is irreducible over Q, right? And
Yes, sir.
this implies uh, the degree of extension of alpha over Q is equal to 3, which is not of the form 2n, and this implies alpha is not constructible, right? Because if it is constructible, then its degree should be of the form 2 raised to n. So in this field is not an example of a field in which every element is constructible, because alpha belongs to this field, but alpha is not constructible. Okay. Now, what about Q6 and Q66 and C7? Xi7, sorry, not C. So this is clear, right? Why alpha is not constructible? Because it has degree 3, which is not a power of 2. Now,
Yes, sir, it is okay.
okay. So the C part is Q Xi 6. Okay, so we just need to see Xi 6 is whether Xi 6 is constructible or not, because Q is constructible, and if Xi 6 is constructible, then any element of the form A plus B Xi 6 will also be constructible. Okay, so that's what we have to see. So although we have already seen this in some some context, but let me just write it. So Xi 6 satisfies,
X6 minus 1 is equal to 0, na, sir?
yes. Okay, so this satisfies the polynomial x6 minus 1, and which is equal to x cube minus 1 x
X6
cube
plus 1.
plus 1, and Xi 6 cannot satisfy this, that we have already seen. Why? Because Xi 6 is the primitive root of unity, it generates all roots.
Mm. X cube plus 1 only.
Only generates uh, cube roots, right? It can only generate 3 roots, but J6 should generate 6 roots. So J6 must satisfy this. J6 must
And
satisfy.
this is also irreducible
Why?
by Einstein criteria.
How you will apply Einstein criteria to this? Which prime you will take?
I think 2. Mm, no, 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 no.
So A naught is 1.
X.
A naught is 1, right? Einstein
Yes,
criteria
I
says that P should divide A naught A1 so on to An minus 1. Which prime will divide 1? So, so we have to do some trick to actually show that this is irreducible. But but at least we know that this is J6 must satisfy it. So now this implies that degree of J6 over Q is less than equal to 3, right? Because it satisfies the polynomial of degree 3. Now, the claim is x cube plus 1 is irreducible. But to show this, what we will do, we cannot apply Einstein criteria in this form. So we will use the lemma. Recall that fx is irreducible on a field f if and only if fx plus a is irreducible on f for all a belongs to f. That we did last time. Proof also we have seen, right? So let's say we give it some notation, maybe gx I can call.
sir,
Yes.
by replacing x with x plus 2 on the equation,
Mhm.
then we get the equation x cube plus 6x square plus 12x plus 9. So when p is equal to 2, it will be also irreducible at that time.
uh, you are getting 9, right?
Yes,
A not equal to 9. Again, how Einstein criteria will you apply?
but when p is equal to 2,
Yes. It says 2 must divides a naught a1 an minus 1 till an minus 1. 9 is not divisible by 2, right?
yeah. A1 and A2 will be divisible only.
That's the case here also. A1 is 0, A2 is 0. They are divisible. We want A naught, A1 and A2 to be divisible, and AN that is that should not be divisible. And also uh, P square should not divide A naught.
Mm. Okay, sir, right.
Okay. So, but you need not to go to 2. 1 will also work. So consider gx plus 1. That is what? X plus 1 cube uh, plus 1. This is, oh, here also we will have some problem, I guess. You know? Yes, yes, yes. Here also we have some problem. So, oh, it is not irreducible. It is not irreducible, I guess. Yes, because see, okay, let me just tell you why it is not irreducible. It actually reduces. We were on a wrong track. So, see, mm, say,
I think, sir, here are two factors. One
mhm,
factor is x plus 1,
yes,
and the second one is x square minus x plus 1.
that is okay. That you might be seeing through the solutions. But what is the means uh, how to like uh, predict these things? Means once you have a factorization, then you can say, oh, this is reducible. But just from this information, how one can directly say that what is the trick behind it? So see, if the trick is if some alpha satisfies x cube minus 1, then minus of alpha will satisfy x cube plus 1. Do you agree? Okay. So this implies so uh, now since xi3 xi3 square and minus 1 sorry 1 are the roots of x cube minus 1, therefore minus xi3 square and minus 1 are the roots of x cube plus 1, and these are of course distinct roots. So this implies x cube plus 1 is actually uh, x plus 1 x plus zeta 3 and x plus zeta 3 square. So yeah, now okay, so Vivek, you have rejoined. So let me just revise what I did. So see, what the trick is, if alpha satisfy x cube minus 1, then a minus of alpha will satisfy x cube plus 1, because minus of alpha, when you put here, this will be minus alpha cube plus 1, and alpha cube from, so let me just say a few, minus alpha cube plus 1 will be minus of alpha cube plus 1. But if alpha satisfies this, that means alpha cube is equal to 1. So this will be minus 1 plus 1, that is 0. So that is the trick. If alpha satisfies x cube minus 1, that minus of alpha will satisfy x cube plus 1. Okay. So that's why since xi3 square and 1 are the roots of this x cube minus 1. So minus xi3 square and minus 1 are the roots of this polynomial. And these are the distinct roots. Thus, x cube plus 1 is of this form. And so it is reducible. Now, this has to be inside Qx because This is because x cube plus 1 uh, and x plus 1 are inside qx, right? So we are just dividing. So this is a real rational polynomial. This is a rational polynomial. So this has to be a rational polynomial, right? That's how you are getting x square minus x, or that thing, whatever is written there. So yes, this is a degree 2 polynomial also. You even need not to uh, solve this explicitly. This is a degree 2 polynomial, degree 2 polynomial, right? Because here degree 1, which is irreducible in qx. Why? Because it has both roots outside q, so it has to be irreducible in q, and thus from here we get that q xi 6 over q is 2, right? Because xi 6 satisfies this polynomial. This polynomial is irreducible polynomial in qx of degree 2. That's why the uh, degree of the field extension q xi 6 over q has to be 2. Clear? And thus each element of this implies each element of q xi 6 is constructible over. Clear? So is constructible. Over q has no meaning. Now let's move to the next question. So I hope this is clear. If there is doubt, then you can ask. Otherwise, we can move to the next part, which is q xi 7. So here again, q is each element of q is constructible. So we just need to see xi 7, and xi 7 satisfies x7 minus 1, which is x minus 1, and x6 plus x5 that we have seen in already seen that. Now this polynomial we saw in one of the lecture. This polynomial is irreducible. Why? Because as an application of not directly by Eisenstein criteria, but using some tricks, we were able to show that as an application of uh, Eisenstein criteria, we showed, we proved earlier that any polynomial, that a polynomial uh, 1 plus x square so on to xp minus 1 is irreducible over q if p is a prime. I hope you remember that proof. Just need to replace x by x plus 1 and then if when you expand it, you will get a polynomial on which you can apply Eisenstein criteria, and thus uh, that is the case. Okay, so this polynomial is irreducible, which implies, okay, so which implies um, q xi 7 over q is p minus 1, and as an application of it, we prove that q xi p over q is p minus 1. So here p is 7, so this is 7 minus 1, which is 6. And of course, this is not of the form 2n, so xi 7 is not constructible. Okay, so that is, so we have option 1 correct, second incorrect, and third this correct, and fourth is incorrect. So that is from assignment number 1. So we can move to assignment 3 now, I guess. Sorry, assignment 2. We've already given a lot of time here, so I will skip some of the details which are uh, easy to see in the solutions of this assignment. So let me just quickly paste the first problem. Let's think. Here we go. The first question is, which of the following are not constructible? So all Gaussian rational numbers. So what are all, what is mean by Gaussian numbers, Gaussian rational numbers? So they are q uh, elements in the field qi, means a plus bi type of numbers where ab belongs to q. Okay, now this is okay because uh, I is constructible and each element of the q is constructible. So since I is constructible, you have each element of, and I is constructible because it lies in a degree 2 extension, right? Q is constructible. All algebraic numbers. So this, on this I will come, and here why this these two are constructible. Uh, this is because, so I will explain, let's say for this. So it is constructible if and only if the angle 2 pi by 5 is constructible and this is constructible if and only if a 5 bone is constructible. So we have already seen that table, and mm, this is true by uh, what theorem? Last time we read one theorem, right? Uh, so any n-gon is constructible if n is of the form, uh, this is true since uh, 5 is of the form 2 raised to 0 times product of Fermat primes, right? So this is a Fermat prime, right? Fermat prime means it is of the form 2 raised to n plus 1. So it's 2 square plus 1. So this is okay, right? And here, since 3 is of the form 2 plus 1, this is also Fermat prime. So here also we will use the same trick, and it is also constructible. Now, what about algebraic numbers? Algebraic numbers are not constructible. Why? Because you can see the example. Algebraic numbers. Algebraic number is a number that satisfy a polynomial in Q. So algebraic number, let so this number is constructible. In, in fact, you can say uh, xi3 is an algebraic number. Simplest of example, xi3 is an algebraic number. So what is why xi3 is an algebraic number? Since it satisfies, no, xi3 won't work because xi3 has extension of degree 2. So xi3 is not a good example to take. Maybe we can take 2 raised to 1 by 3 or 3 raised to 1 by 3. Anything will work. It's an algebraic number since it satisfies x cube minus 2 over q, right? And this polynomial is also irreducible by Isestian criteria. Um, but uh, q of 2 1 by 3 over q is what? This is 3 because you have a degree 3 polynomial which is satisfied by it, and it is irreducible. This is also not form of this form. Okay. Okay, so this implies that 2 1 by 3 is not constructible. Not constructible. In general, so in general, we can take any algebraic number in general. In general, any algebraic number for which the minimal polynomial, the degree of the minimal polynomial, degree, the minimal polynomial is not a power of 2 in a general any algebraic number for which the degree of the minimal polynomial is not a power of 2 uh, is not constructible. Okay, because you will not get uh, a degree two extensions, tower of degree two extensions. Okay, so now yeah, this is the first question. Let me write the second one. Okay, so it says consider the field F and an extension E of F of degree 2 and an extension D of E for alpha belongs to D. What are possible values of E alpha over F alpha? Okay, so what is the situation here? Here you are having two fields E and F. Okay, let me just try to explain this using tower of fields. You have F in the bottom, E you have as a subfield, sorry, superfield. Yes, you are right, it is 2, but one has to show. Uh, so F, then you have E, then uh, you have D somewhere, which is also a superfield of this, and alpha is inside D, right? So alpha may or may not be inside these fields, but alpha is there. So definitely, okay, that won't be a right way to say, I guess. This will be, so E of alpha will be there between D and E, right? Because alpha is there inside D, right? So E E is contained in E alpha, and E alpha is also there inside D, because E is inside D and alpha is inside D. So this is situation, and of course you have f of alpha, which is also an extension of uh, D, and this is also contained inside this. Okay, because uh, E alpha contains F, because F is contained in E, and then it also contains alpha. Okay, so that is the situation. Now just try to use this much of information to actually conclude whatever we want to conclude. So this, how can we use this? So it says that E has degree 2 over F. So this has degree 2, right? So this thing we have to use. So see, E of alpha over F. So from here to here, this tower we have to use. This has degree E alpha over E here to here, and then multiplied by E over F. Okay, this is one way to calculate this degree. The another way is go through here. So this is also equal to E alpha over f alpha, and this times E f alpha over, right? So now what? Now what values we are given? We are given this value that E over f is 2, right? And we have to calculate this, but we have to also compare E alpha E and F alpha F, right? So what is the degree of E alpha over E? So E alpha over E, this is nothing but from here to here, this is nothing but the degree of minimal polynomial of alpha over E, right? The minimal polynomial that is satisfied by alpha. And what is F alpha F? This is the degree of minimal polynomial of alpha over F. Here we have E, right? Okay. Now since E contains F, therefore the degree of E alpha over E has to be less than the degree of F alpha over F. Why? Because this is because if uh, if a polynomial is irreducible over the larger field, that is E, then it is irreducible over F, because you cannot split it as factors of as polynomials in E, and F is contained in E, means you cannot like split it in F also, right? But the converse may not be true, right? You are not able to split it in a smaller field, but after going to a larger field, you may be able to split it. Like you can take Q over Q, you can take x square minus 2, and if you take an extension of containing root 2, then you can split that in a Q root Q adjoint root 2, but you are not able to re reduce it in Q. So over a larger field, the polynomial may split, but if it is not splitting on the larger field, then it will not definitely split in the lower field. Okay. So that's the reason that a polynomial is irreducible over E, then it is irreducible over F, but the converse may not be true. That's why it is less than equal to this. So because if you find a polynomial here that is uh, minimal, then it will be minimal as a polynomial, then it will be reducible as a polynomial here also, but the converse is not true. You may require a larger polynomial here which is satisfied by alpha. Okay, just you can take the example of uh, root 2 here. So if it is q root 2 and it is just q, so here you need x square minus 2, but here you can just take x minus 2, x minus root 2, because root 2 is there inside the field. Okay, so this implies that using this thing, what you have, this is less than equal to this. So let me write it as equation 1. From 1, from 1, this implies that the degree of uh, E alpha F alpha is less than equal to the degree of E over F, and which is 2. So this implies the degree of E alpha over F alpha is either 1 or 2, right? So that's the idea behind it. Okay, so maybe we can move to the next question. The next question says that which of the following, I have to paste here also. Yeah. So which of the following polynomials over Z 3Z mod T is has repeated roots in some extension of Z mod 3Z? Okay, so solution. So last uh, we have seen a lemma which says that that's a recall part. Recall, let F be any field and Ft belongs to capital F of T has no repeated roots if and only if the GCD of Ft and the derivative of Ft, yes, you're right, uh, Vivek, this is one, right? So we have to just compute the GCDs and compare, right? So the first in case we have Ft to be T cube minus 2. What is D of Ft? This is you just 3t square, right? But this is equal to the zero polynomial in Z mod 3zt because it in Z mod 3z t 3 is equal to 0, right? So that's why here the GCD is the polynomial itself. It is not equal to 1. This is this which is not equal to 1. This implies Ft has repeated roots. Z mod 3z. This much is enough. Even if you want to verify this, you can verify because here this is a polynomial of degree 3. So a polynomial of degree 3 in Z mod 3z you can see means it has to be like um, so any degree 3 polynomial is reducible means it must have a linear factor. So if it has a root, then it has a linear factor in Z mod 3z and then you divide it by that factor, you will get another linear factor. Uh, you will get a degree 2 polynomial and there you can see it will have some repeated roots either in Z mod 3z or in some extended field. But anyway, we need not to do all that calculation. We have this lemma. So because that calculation fails once you have this kind of polynomials of higher degree t. So here you have t5 plus 2t. Ft is, I should use some other color, I guess. T5 oh, t5 plus 2t. And what is d of ft then? This is nothing but 5t4 plus 2, right? Then uh, this is what? This is same as so can you say something whether they have a common factor or not? I will say no, they don't have. So why it is the case? So you should divide it and then see whether they are having a common factor or not. One way is this. The second way is to split this polynomial in linear factors and then check whether you are getting the same factors or not. So this is a time consuming process to see actually that these two factors, these two have no factors in common. So in Q they won't have factors in common because you can apply Einstein criteria or any of them. This is also irreducible in Q and this is also irreducible in Q, but as Z3 you don't know whether this is reducible or not. But see, one thing you can do, you can take T from here and this will be T4 plus 2, right? So and this is what? This is uh, isomorphic to 2t4 plus 2, right, in Z3t, because 5 is congruent to 2 in Z3, right? So how this will help us? So this is nothing but t4 plus 2 and then you have t4, right? So see, it has t equal to 0 as a root, but this polynomial, this do not have t equal to 0 as a root. Okay, so definitely t is not a common factor. So this implies t5 plus 2t and 5t4 plus 2, their GCD is same as, you can take t from here, t4 plus 2 and t4 plus 2, oh sorry, plus t4, right? So what I have done is this has two factors, t and t4 plus 2. This t is not a factor of this, so I can, while taking GCD, I can just ignore it because this is not going to be a common factor with this. So I will just go with T4 plus 2, and then 5T4 plus 2 is same as T4 plus 2 plus T4 in Z3T, right? So this implies, so from here, can you say something? See, if this implies if alpha satisfies T4 plus 2 in any extension of Z mod 3Z. So it might happen that the root is not inside Z mod 3Z, but we know that there is an extension which contains all the roots, right? That is called a splitting field. So if it is not inside T4 plus, so if alpha is anything that satisfies T4 plus 2 in any extension of Z mod 3Z, and okay, before that I need to just write one more line. So this implies if T4 plus 2 and T4 plus 2 plus T4 has a non-trivial common factor, I need some more space, say GT, okay, and I will write it again, no issues. So, and uh, if alpha uh, satisfies GT, alpha belongs to some extension of Z mod 3Z, okay. This belongs to some extension of Z mod 3Z. So if it is satisfied GT, then it must satisfy uh, T4 plus 2 and T4 plus 2 plus T4. It must satisfy both T4 plus 2 and T4 plus 2 plus T4, right? Because GT is a common factor, so GT will divide this and GT will divide this, right? So uh, that means what? Uh, so if there is some root of GT, that will also be root of this, and that will also be root of this, right? And there will be a root of GT in some extension of Z mod 3Z. That also we know. So if there, so for any root of GT, it will satisfy T4 plus 2 and T4 plus 2 plus T4 also. This implies uh, it will satisfy their difference also. It instead of twice, this implies alpha will satisfy T4 plus 2 plus T4 minus T4 plus 2 also. If root something is satisfying this polynomial and something is satisfying this polynomial, they will satisfy, it will satisfy the difference also. But what it is, this is just nothing but, so alpha will satisfy the difference is T4. And what are the roots of T4? This is nothing but alpha is 0, right? And that is a contradiction, right? So this implies but 0 does not satisfy T4 plus 2, because this will, after putting 0, this is 2. This is congruent to uh, the, T4 plus 2 plus T4. Okay, I will re-explain it. Okay. So it let me just first write it clearly, but 0 satisfies neither T4 plus 2 and nor T4 plus 2 plus T4 in Z mod 3Z. And this is a contradiction. Thus, GT has to be a constant polynomial and which implies the GCD of T4 plus 2 and T4 plus 2 plus T4 is equal to 1 in Z mod 3Z T. Okay, and that is same as the GCD of 5T4 plus 2T. Okay. Yes, 5T4 plus 2T and 5. Oh, what was that? T4 plus 2T, T5 plus 2T. This is T5 plus 2T. This is the same as the GCD of T5 plus 2T and 5T4 plus 2. So this implies T5 plus 2T has no repeated roots. The lemma says that it has limited roots if and only if there is no repeated roots, if and only if the GCD is 1, and here the GCD is 1, that's why it has no repeated roots in Z mod 3ZT. So yeah, so I will re-explain it, no worries. So we have to see in everything in Z mod 3ZT, right? So if this polynomial would have been considered as a polynomial of Q, then definitely we can apply Eisenstein criteria here and say that uh, uh, it is this polynomial is reducible, right? This polynomial is definitely reducible because T is a factor of it, but this polynomial is reducible. We can apply Eisenstein criteria directly. A naught is 2 and A1 is A1, A2, A3 are 0. So you can apply the Eisenstein criteria and see that it is reducible. Here A naught is 0. So whatever prime you take, its square will definitely divide 0. Okay. So, but this is irreducible over Q. But the main problem here is we are not inside Q. We are here inside Z mod 3Z. So we cannot use Eisenstein criteria here. We have to see without using that whether these polynomial have some common factor or not. So what I did, so T5 plus 2T, you can write it as T times T4 plus 2. And then this you can write is 2T4 plus 2 because you are in Z3, so 5 is congruent to 2. And that is same as T4 plus 2 plus T4, right? So yes, so their GCD is same as the GCD of t. So it has t equal to 0 as a root, but this polynomial has don't have t equal to 0 as a root. You can directly put t equal to 0 and you won't get 0 here. So it don't have t equal to 0 as a root. Okay. So while taking GCD, I can remove t from t5 plus 2t. So that's why I put here t4 plus 2, and then 5t4 plus 2 I can replace by t4 plus 2 plus t4. So they have the same GCDs, this pair and this pair. Now suppose that they have a non-trivial common factor, say gt. So it will have some root in some extension of Z mod 3Z. We have seen that if gt is a polynomial in ft, then it all of its roots lies inside some extension of f. So it will definitely have a root in it in one of the extension. So say it has al alpha as a root. So if alpha is a root of gt and gt is a common factor of these two, so alpha should satisfy these two polynomials also. That's what I have written, that it must satisfy both t4 plus 2 and t4 plus 2 plus t4. Then alpha must satisfy their difference also, but their difference is what? Their difference is t4. So alpha will satisfy t4 if and only if alpha is 0, right? But 0 satisfies neither t4 plus 2 nor t4 plus 2 plus t4 in Z mod 3Z. Thus, this is a contradiction, and gt has to be a constant polynomial, because if it is not a constant polynomial, then it will have a root in some extension, and then you will have the contradiction. So that's why the common factor has to be a constant polynomial, and thus their common factor their GCD is 1. Understood? Okay, fine. Thus t4 plus 2t has no repeated roots in Z mod 3Z. Okay, so that's an interesting question. So now let's move to the next part, C, which says this is ft equal to tq plus t square plus t, and d of ft will then be 3t square plus 2t plus 1. Now, this is congruent to 3t square is 0, 2t plus 1 in Z mod 3zt, right? And 2t plus 1 is also uh, mm, congruent to minus 1 times t plus 1, right? In Z mod 3zt. Because 2 is minus 1, and that is, if I take minus common, this is nothing but t minus 1 in Z mod 3z. Okay. And here also you can check, uh, one satisfies this polynomial also. Oh, no. Maybe I'm doing some mistake. Yeah, 1 satisfies, right? Because this is 1 cube uh, plus 1 square plus 1. So this satisfies t cube plus t square plus t in Z mod 3z t, right? 1 plus 1 square plus 1. Okay. So this implies that t minus 1 uh, divides, t minus 1 is a factor of t cube plus t square plus t in Z mod 3zt. So here it is just t minus 1, it is t, and t minus 1 is a factor of this. So what is the GCD? The GCD of t cube plus t square plus t and minus t plus 1 is nothing but t minus 1, right? Yes, you are right, Vivek. Which is not equal to 1. This implies it has repeated roots. This implies um, ft has repeated roots. I should not have used this color. This is very uh, okay. This I can. What about the next part? So let me move to the D part. So D part is ft is t6 minus 1. So what is d of ft here? D of ft is 5t, sorry, 6t5, which is congruent to 0 in z mod 3z t, and thus GCD of ft and dft is the polynomial itself, t6 minus 1 not equal to 1. This implies t6 minus 1 has repeated roots in z mod 3z t. Okay, so that's question number 3. I hope that is clear. Let me quickly move to the next question. Okay, so question number 4. 14 or what? Oh, oh, it's not coming. Let me just repaste it. Yeah, here it is. So it says use Euclid's division algorithm to determine which of the following polynomial in Qt is not uh, do not have a uh, repeated root, or it have a repeat. So we just need to do the same thing as last question to check whether D, Ft and Ft have some roots in uh, some whether DFT or FT has a non trivial GCD or not. Okay, so yeah, so the first question is ft is equal to, so ft is equal to tq minus 4t square plus 5t minus 2, and dft is nothing but 3t square minus 8t plus 5. So I will do the division thing for one question, and then others you can try. So we have to use the Euclid's division algorithm, means we have to like divide this polynomial by dft. So 3t square minus 8t plus 5, you have to uh, do the division, tq minus 4t square plus 5t minus 2. The division as polynomial. Okay, so how we used to do this division? Divide this first leading coefficient, divide this leading coefficient by this 3t square. So t cube by 3t square is what? This is equal to 1 upon 3 t, right? So this 1 upon 3t will come here, and then this I will keep as rough so that you can see what is happening. Then this 1 upon 3t is multiplied by the entire thing, 3t square minus 8t plus 5. So what we did, we just divide this leading coefficient by the leading coefficient of this, got 1 by 3t, and then we multiply this leading coefficient, this answer to this entire polynomial, and then subtract. So 1 by 3t multiplied by this is t cube minus 8 upon 3 t plus 5t by 3, and we will subtract this. So this this and this will cancel out. This will give you how much? This is minus 4, and this is plus 8 by 3. So this is minus 4 by 3 t square, and then 5 minus 5 by 3. This is plus 10 t by 3, and then you have minus 2 as it is. Again, do the same thing. Maybe I can just circle this leading coefficient and leading coefficient we do, then again leading coefficient, and what it will give you, this will give you um, minus 4 by 3 t square divided by 3t square. So this is minus 4 by 9. So minus 4 by 9 will come here, and then this 4 minus 4 by 9 has to be multiplied by this entire polynomial, and this will give you minus 4 by 3t square plus 32 t by 9 and minus 20 by 9. Change the signs. Okay, this will be cancel out. This you will get minus 2t by 9, and this is 2 by 9. Okay, so all this calculation implies your t cube minus 4t square plus 5t minus 2 is equal to 3t square minus 8t plus 5 times this one 1 by 3 t minus 4 by 9, and then you have plus minus 2t by 9 plus 2 by 9. Okay, now what we will do, we will now proceed with this thing, whatever is the reminder, this reminder, and this thing, right? So this is the dividend earlier. So because that's what Euclid division algorithm says, na? If you want to find the GCD of A and B, then write A as BQ plus R. If R is equal to 0, then fine. If R is not equal to 0, then write B as some B dash Q plus R dash. If R dash is 0, then fine. Otherwise, proceed the same with B dash and R dash, right? That's what we are doing. So now we have to divide. We have to take this minus 2t by 9 here and plus 2 by 9, we have to divide it. Mm, mm, this thing 3t square t minus 1 is a common factor. Yes, you are right. So it will divide completely, and you, you can see that when you divide the leading coefficient this by this, it is you will get minus 27 by 2 t. Multiply this by this will be 3t square minus 3t. Change sign, this will be cancel out, this will be minus, sorry, yes, minus 5t plus 5. Again, leading coefficient, this you will divide by minus 2t by 9. This will be nothing but 45 by 2. Yes, 45 by 2, and again they multiply it and you will get minus 5t plus 5, and that will change sign, it will give you 0. Okay, so this implies that 3t square minus 8t plus 5 is minus 27 by 2 t plus 45 by 2 times minus 2 by 9 t plus 2 by 9. Okay, so you can replace this part by here and you will see the GCD is this minus 2t by 9 plus 2. So if you get 0 at some place, that means the whatever with whatever you were dividing, that will be the GCD. So this implies the GCD of t cube minus 4t square plus 5t minus 2 and 3t square minus 8t plus 5 is nothing but minus 2t by 9 plus 2 by 9, but this is up to the units, right? So units you can take. So 2 by 9 is a unit, so you can remove it, and the here 2 by 9 is also unit. So you can multiply both sides by minus of 2 by 9, sorry, minus of 9 by 2, and you will get t minus 1. So this is the GCD, but you can multiply it by minus 9 by 2 because it's a unit. So you will get t by 9, which is of course not equal to 1. So this implies t cube minus 4t square plus 5t minus 9 has repeated roots. What was the field in consideration? Qt. Yes. Okay. So that is the idea in Qt. Okay. So the next one I can simply write, and you can just check your calculations. So B1 B part is ft is t cube plus 6t square plus 11t minus 6, and here you have 3t. D of ft is thus 3t square plus 12t plus 11, and so uh, when you divide it with 3t square plus 12t plus 1, you will get that t cube plus 6t square plus 11t minus 6 is 3t square plus 12t plus 11 times um, t plus 2 by 3, and you have in addition to that 2t, sorry, minus 2t minus 4t by 3. Minus 6t square in the second term. I couldn't get you. You are saying for this or the last one, Vivek? Uh, okay, anyway. So this is, you are saying the question is wrong? Oh, it is minus 60 square plus 11t minus 6. Oh, so I did it by considering it minus plus 60 square. So yeah, means similar kind of thing will happen. Maybe we can see for the 60 square, and for minus 6t you can see. Okay, I couldn't I realized it while calculating it. Thanks. Anyway, means I will just write for plus 6 and you can check for minus 6. Okay, so uh, this is the not equal to 0. So here you have again you have to do the division. So then you can check 3t square plus 12t plus 11. I'm sure that the calculation will become easier once you have minus 6t square. But anyway, uh, you have to divide it by this. So this is minus 2 by 3 t plus 20 times this is uh, you will get minus 90 by 2 plus 72 plus 949. Okay, so this is not equal to 0. So GCD is now this 949 up to units. So up to units, that means 60 square plus 11t minus 6. It has GCD 3t square plus 12t plus 11. It has GCD 1 because it is a unit. Okay, so this implies t cube plus 60 square plus 11t minus 6 has no repeated roots. So similarly, you can do the other two parts. I will just write what the solution is. So ft is t cube minus 5t square plus 8t minus 4, and d of t is 3t square minus 10t plus 8, and you need to check that here GCD of ft and dft is not equal to 1. So repeated roots will be there, and in the D part D part will have ft to be t cube minus t square minus 2t plus 2, and dft will be nothing but 3t square minus 2t minus 2. Here the GCD will be 1. Check that the GCD of ft and dft is 1. So we have no repeated roots. Okay, so I will rush to the next question. So next question is also of the same nature, but here we are given the liberty to uh, do it by any method. We are not forced to use Euclid's algorithm only. So we will use various tricks. Which of the following polynomials, cubic polynomials, are in Qt have repeated roots in some extension of Q? So now this question is interesting. So A is t cube minus t, right? And let me write ft is t cube minus t. So what is d of ft? D of ft is 3t square minus 1, right? So this is say t, you can t minus 1, t plus 1, right? So if they have a common factor, then uh, 0, 1 or minus 1 should satisfy this, right? So df of 0 is, you can check that df of 0, df of 1 and df of minus 1 is not equal to 0. Yes, not common factor is not equal to 0. This implies that neither 0, 1 or minus 1 is a factor, thus they have GCD to be 1, which implies no repeated roots. What about second? So for second also, you can use this root thing. Ft is t cube minus 2t square minus t plus 2, and dft is 3t square minus 4t minus 1, right? So let's consider this thing. I used used. Yes. So this has roots t equal to, use the binomial root, this quadratic formula. So this will have roots or instead of calculating its roots, maybe the easier thing is to find the root of this. Let me focus on ft first. So see, f of 1 is equal to 0. 1 minus 2 minus 1 plus 2. This implies t minus 1 is a factor. So t cube minus 2t square minus t plus 2, when you divide it by t plus 1, you will get t, sorry, t minus 1, you will get it t square minus t minus 2. Okay. Now they have roots equal to 2 and minus 1, that you can check. But again, d of f1 not equal to 0, d of f minus 1 not equal to 0, and d of f2 not equal to 0. So they don't have, so this DFT don't have these roots. This implies that they don't have a common factor, and DFT is equal to 1. So again, no repeated roots. Okay. Similarly, you can check the other two, I guess. Okay. So I'm leaving it to for you, that check C and D similarly, because we have done enough questions of such find. So I hope you can do this, because you can use the same thing, same trick. Okay. In the other two things, there will be a common factor, right? Uh, you will find a common root. So it's better that we do something else, right? We are just doing the same question again and again. So I will, the sixth one says the polynomial 2x cube plus 49x square plus 21 plus 63 is irreducible in Qi. So the similar kind of question we have done in lecture notes, and also in the last um, session also. So let's say I said fx. So fx is irreducible in uh, Q. Yeah, by Isestian criteria, right? For p equal to 7, you can see. So uh, now if fx is reducible in Qi, then fx must have a root in Qi, because it's a degree 3 polynomial. So at least one of the factors should be linear, must have a root in Qi, say to be alpha, then what you have? You have this situation, Q I contains Q, and it also contains alpha, and then it contains Q, right? But here to here, you have degree 3, since alpha satisfies fx over Q, and this is also irreducible. Okay, so degree 3, but here to here you have degree 2. So this is a contradiction, right? So this implies fx is irreducible over Qi as well. Okay. This thing we have seen number of times. So I will move to the next question. Next question is interesting. I will give some hints. No, roots in Qi or Q both have same meaning. No. See, roots in a field means, in general, you are asking, in general, it is not. But for a degree 3 polynomial, you can use the same trick and say ki yes. If it is a degree 3 polynomial, then degree 3 polynomial which is irreducible in Q, then you can use the same trick. Roots meaning that there is an element in that field which satisfies this polynomial. For example, if instead of this polynomial you would have x square plus 1, then x square plus 1 is irreducible in Q, but it is reducible in Qi, because x square plus 1 is satisfied by I, which is in Qi, but it is not in Q. So This is due to the nature of the polynomial that we are getting, that it is irreducible in Q, and we are using that irreducibility to actually conclude that it is irreducible in Qi also. Okay, roots having means it is satisfied for only degree 3 polynomial or greater, only for degree 3 polynomial, or maybe no, for any polynomial of larger degree also it will work if it is irreducible in Q. We will just use this tower. So even if it's a degree 5 polynomial, or maybe not, maybe not. Wait a moment. Wait a moment. No, that this degree 3 polynomial is a special case. Yes, because see, in degree 4 polynomial, you may have reducibility as in the sense that it splits into two polynomials of degree 2. So it may not have a root, but still it is reducible. Okay, but degree 3 polynomial is reducible means it must have a root, and that thing we are using here. So for higher polynomials it may not hold. Okay. Okay, so yeah, so now let's move to this seventh question. So we have been running out of time, so what you want, we should finish it quickly this time, or we should continue it next time? Vivek? Vivesh or others, anyone can say. I think in the next session. Okay. So then I will just explain this seventh part, seventh question, and then the remaining ones we will see in the next session. You know, I will try to be less expressive in the next session, because I think we have covered a lot of theory here only. So it's just a matter of solving questions with some tricks or something. So I will be very less expressive in the next session uh, for this assignment, because in the next section I will also try to revise the notes of week 3. Okay, so let's just finish this question and then we will stop. So yeah, this okay. So this is irreducible in ZX. This is same as if we see the irreducibility in QX or ZX, because by Gauss lemma we know that it is in, if it is irreducible in QX, then it has to be reducible in ZX and vice versa. So, but we cannot apply Eisenstein criteria here, right? Because Eisenstein, because the A naught term is -1 when there is no P which is dividing it, right? I think we should do mod n for some n. Okay. Mod n thing gives you Eisenstein criteria, right? So how will that be useful? So because from mod P only you will get the proof of Eisenstein criteria. Eisenstein criteria is not applicable. If that for mod n, you have to tell me the n, like for which n you are thinking that it will work. So what I will do, as we usually do, that if Eisenstein criteria is not applicable directly, then we try to apply it on x plus 1 and see what is happening there. So the same thing we will do here also. So consider fx plus 1 and see if it is irreducible or that. or reducible, because fx plus 1 is reducible if and only if fx is reducible. In fact, in place of 1 you can replace it by any other integer. Okay, because here underlying thing is z. So yeah, fx plus 1 is what? X plus 1 cube plus sorry, minus 3x plus 1 minus 1. So you can see that this is what? This is x cube plus 1 plus 3x square plus 3x minus 3x minus 3 minus 1. So 3x to 3x get cancelled. 1 to minus 1 get cancelled. This is x cube plus 3x square minus 3. Yes, you're right. So now we can use Eisenstein criteria. Use Eisenstein criteria for p equal to 3. So the of course 3 divides minus 3 and 3, and p square here does not dividing minus 3, and p square is also not dividing 1. So this implies fx is irreducible. Fx plus 1 is reducible. That will imply that fx is reducible over zx by Eisenstein criteria. Okay. Okay then. So any doubts or anything? If not, we will stop here, and we will continue from question 8 onwards in the next session, and we will try to revise uh, some part of V3 also, if not the full part. Okay. Okay. So thank you. We will. Okay, others, you are commenting something. If it is irreducible, if it's reducible, it must have at least one linear factor, and since it's monic, it must be root in uh, z. That's fine. In root in z and root in q are same. If we do mod 4, image is minus 4 minus 1 minus 1, hence it has no solution. So couldn't get. You are you want to do mod 4 uh, to with this polynomial. So this will, in mod 4, this will be x cube minus x minus 1. Or what means I couldn't understand. Okay, you are saying that if you apply, okay, okay. If it is reducible in zx, then it is reducible in z4x also. And since it is QB polynomial, it must have a yes, it must have a uh, root in Z4, and that means if you apply 0, 1, 2, 3, all these things uh, to this polynomial, it must give 0 for some value, right? So if I applying 0, then it x equal to 0, then it is minus 1, x equal to 1, this is minus 3, which is yes, 1. Yeah, if x equal to 1, then this is 1 minus 3 minus 1, which is minus 3. Okay, and if x equal to 2, then this is 8 minus 6 minus 1, which is yes 1. And yeah, x equal to minus 1 will give you minus 1 minus 1 2. Yes, yes, you are right. Then it will all again 1. Yeah, that way also you can do. Very good, Adarsh. So this is also a solution, as Adarsh pointed out, that we can see this also as a as considering it in Z4x and it has no root in Z4. That's why it is irreducible. This way also you can do. Okay. So cubic polynomials are special cases. You can, of course, take it in n modulo case, and there, if you are not having a root, then it will be irreducible. Yes. Good. Good, Adarsh. Good, Vivek. So, any other comment or doubt? If not, I will stop here, and we will meet uh, on next Tuesday. Okay. Okay.